I'm the second president, Li Fenghan. This is a work for my student, Han Yu, who did a master thesis with me last year. Now he already works in a company as a research engineer in China. And I think he's well paid, so he decided not to do a PhD. And so we wrap up on his thesis actually. And his thesis is about extraction of medication and temporal relation from clinical text using neural language models. We call it neural language models because we try to investigate the different models instead of specific one. And this work is was based in University of Manchester, Natural Language Processing Group, but our group heavily emphasized on healthcare text analytics. And my promoter is Goran. So I will introduce, starting with motivation and the key findings we received, and then the project we call it Make Time, milestone 1. Later I'll give you a surprise, and then the experiments and some discussion. So, like Matteo mentioned, electronic health record is the focus of this work that we do text analytics. And just one small thing, when Matteo mentioned the first highlight of the data aggregation, actually recently we had a NeurIPS synthetic workshop paper. We generate synthetic data for clinical text mainly. That might be interest to any of you if you would like to try, because our tool is open source on GitHub. You generate the synthetic data in clinical domain, and we deploy it in the tasks. Okay, for this paper, we do two tasks: one medication extraction mostly, also some with problem detections, and then temporal relation, because temporality is one interesting thing that can help the clinicians to better understand patients' problem, treatment, and progression. For example, with different time slots when the patient visits the hospital, how the treatments change and how the problem progress or the treatment progress. That is why we want to do this task with Han Yu. And the key finding is we use the CNN by RSTM, CNN convolutional neural networks, and we compare with traditional by RSTM CF that has been set up before transformers. On I2B2 2009 for name entity recognition, and the CNN by RSTM actually won the by RSTM CF model. And for the second task for temporal relations, we tried the birds with CNN. Actually, not many people use bird with CNN. That's something different that we did here. And we use bird CNN to model temporality, like whether this drug or treatment was unused or not during the admission time. For example, when the clinician write down letters for patient, sometimes they write messy or sometimes write different things. They might discuss some treatments or medications, but it's not necessarily that treatment was used during the admission time. So that is this task. So for this task, we designed this project called Make Time. I designed it actually medication mining with temporality with the clock on top, and to evaluate the performance of deep learning models and large language models. That's what we want to try. And the experiment mentioned including BioRSTN, CF, CAN, BERT, that is investigate. For that side, we use I2B2 2009 and 2012 to make it more generalized, because we don't want overfit the system into one shared task. And then when you try another data, it sucks. For NER task, there are different entities, including medication, dosage, frequency, mode, duration, reasons in 2009. And in 2012, there are clinical department, there are evidentials, clinical text, problem, and occurrence. For temporality, I mentioned it's mostly decide whether this treatment was used. This is a pipeline of the framework. So from left to right, from up down. So in left, there's so in the middle you see there's clinical text fit into pre-processing, and after pre-processing there's time expressions and event recognition, After you recognize these events, then there's relation extraction. And after relation extraction, we do post-processing to generate a nicely looking table. And for pre-processing, in the first type, we did the sentence segmentation, tokenization, part-of-speech tagging, parsing, all these feature extractions. And then for time expression and event recognition, that is the CIF, the BioRSTM models that apply there. And then for relation classification, we use BERT and CN. Is it clear or not? Please feel free to interrupt me anytime, because I don't want to miss your answer. And so here is the example. In this piece of text, what we want to extract in the end is there's the ID of this event, the starting date and stopping. So there's admission date and discharge date. And during this phase, the status of this treatment is on or off. That's the temporality part. And this, when you extract the table, if you look at the result, it will be interesting because some of the discussed or mentioned treatments or medications in the letter actually were not used. They just discussed, for example, there might be different possible solutions to treat this problem, but they did not necessarily use all of them. So this information we want to support the clinicians to better understand the patient history, because if they read the letter, they might see a lot of medication treatment, but not all are used. That's the first thing we think is useful. The second thing is, for data analytics, if we want to build a model to learn something about patients, we want the model to know what was actually used, what was not. So that I mentioned. And here's an example about the 2009 data. You can see the text is in the left, the model learned, and the meaning is medication dosage frequency, etc. And there are examples, for example, Hocosex, if my pronunciation is too wrong, and the dosage can be 3.2 milligram. And duration can be 10 days course. And in 2012, that site, there are more categories, for example, clinical departments, including emergency room, and then events that have evidential nature, for example, CT shows or whatever shows. And the symptom can be sickness or can be very specific. Occurrence can be he was readmitted for something, or he was first admitted or something. Evaluation citing, we did a broad evaluation including macro, weighted score, and micro. For whoever is not familiar with the evaluations, for macro, it treats each label the same weight. For example, in electronic health records, the majority of the tokens can be context instead of keywords. So the context, this old label, let's say, can be a heavy weight. But if you use a macro evaluation, this context have same weight with specific category. And then micro actually give each token same weight, and weighted score is each category is weighted according to the population, how much population is occupied in the text. So depends on your specific applications, you might prioritize specific evaluation to make it more meaningful. And here is another table to show model parameters we use for BioRSTM CIF. And then a brief result on macro. This I call it BL strict, because so not only we need to recognize category, sometimes if it is a span, we also ask the model to recognize if it's the beginning of span, or inside the span, or outside the span. And here we draw the figure of learning, model learning loss, and CIF accuracy, how it progress. And this is the score that we get from 2012 that site on the AR part. You can see on some category, it achieves much better than other category score. For example, it can be precision is 1 and evidential, but occurrence it is 34. So from our understanding, the model performs much higher if this token have a bit higher ratio in the data site. But if the token or if this category is a very lowerly represented token, the model struggle to learn it. That's also why I connect with Matthias mentioned in the challenge, the data augmentation is important. We need more samples for the model to learn the specific tokens. It's a learning curve for this 2012 data. And then another experiment we did, we want to examine different kind of embeddings, because nowadays people can choose different word embeddings, and we want to see which one is better for this task. And interestingly, word2vec, that is from around 2013 that was proposed, it performed better than one-hot and close embedding that we that we tested using BioRTM CIF model. And then after we choose this word2vec embedding that's one others, we apply the same embedding into the other models, including CNN BioRTM. Is it clear so far? I'll wrap it also. So here you can see that the CNN BioRTM is one's BioRTM CIF with around 17 points. That's really big gap. And these parameters are scaled. And then for temporal relations, here is the structure that we implemented. In the lower part, you see the birth model, and on top of birth, we fit into the CNN, and then we add the classification layer and move to the output. Parameters are skipped, and here is the interesting part about that sample. So when data is very imbalanced, you can try to teach the model to learn something using sampling, either upsampling or downsampling, to make the data more evenly distributed. That's the one we explored here. We try this on training data, and then we deploy on the test set. We use the real test set. And here you can see on the training side, when you do the sampling to better populate data, the precision required F score really high, like 95 around. And then on the test set, we didn't manipulate anything. We keep test set. Here you can see the macro average is 65 F score. Of course, weighted average 74. The difference here, if you remember it, is the weighted one give each category the weight according to the population. So here, probably we labeled the context very correctly. So the context actually have higher weight, and the special token have lower weight. So the weighted average score is 10 points higher than the macro average score. In summary, we use the CNN BioRTM. It wants BioRTM CIF models and the I2B2 2009 clinical NER task. And we have the exact scores that you can try our tools to compare with it if you want to build on top of it with anything else. And then we use the CNN model. It produced reasonable evaluation scores for temporal relations. And we think temporal relation is interesting task that deserve to be further explored, because so far there are not many works about temporality modeling in clinical domain. And the code, GitHub code, it is in the PPT. So HECTA, HECTA is Healthcare Text Analytics. UM is University of Manchester. And then this project is MedTime. And here is a surprise. One thing I want to say: we have MedTime 2.0 actually this year. my another students from computer science department tried prompting engineering. That is, everyone wants to try either prompt GPT or ChatGPT or whatever GPT, and he got interesting results, and he got this publication in ACL's student research workshop as undergrad students. Yeah, so grazie mille.
So thanks for the presentation. Do any of you have any questions? There's one
Excuse
question.
me. Thank you very much for the presentation. It's interesting, not only the paper but the whole project. Okay. So thank you very much.
Now we have made time 3 actually.
Okay, just one curiosity. Have you developed any deep learning model combining the data from the tasks you got from the natural language processing together with any other data in the electronic medical records?
That's very good question. Can I go to the web browser or not? If I could, this connect to internet, right?
I think so, yeah.
Okay, let me show you.
Yeah, just to finally you've been able to integrate the data from not natural language, not handwriting or not handwriting data from doctors, but any other data that you may find in medical records, such as laboratory tests or any other data, and integrate with the tasks that you gather from your natural language processing.
And you need to move it to the Java. You need also to
Stop share this one.
move.
Okay, yeah.
Use.
Yeah. So this is the work we did about the synthetic data generation. Actually, we combined the data. So the framework is generating medication prescriptions for healthcare NLP, but in the experimental part, here you can see. So we use synthetic data, we use real data, and then we use synthetic data to augment the real data.
Synthetic data?
Yes. The synthetic data that you don't have any concern about privacy and anonymization issue. So the synthetic data actually achieve, if you only use synthetic data, actually it can achieve a 96 F1 score. That's really close to the real data 98 F1 score. But you can still use synthetic data to augment the real data for this task. So that is work I was mentioning when Matteo said about the data aggregation.
You use the synthetic data to train the model?
So we train the model using real tests on the real test side. We train the model using synthetic test on the real test side, the same data side from the shared task. So either you train from the real data or train from synthetic data. So the real one you trained get a 98 F1 score. The synthetic trained model actually achieved 96 F1 score on this task, on the drugs and adverse drug effects related entity extraction.
Okay.
And then if you add on top of the real data, for example, 100% real data, you add 100, 200%, 300% of the synthetic data, and it performance change.
Okay.
So if the synthetic can mimic the real data, then
I know. I know.
Yeah. I think we also have one last quick question.
Just one quick question. So you generated the synthetic data based on your real world data set, correct? Or is it a completely different seed data set for the synthetic data?
Based on real data, not the whole real data. So the whole real data have the context that what this patient come, he has blah blah blah, and then the real data also have a dense part about the prescription. So we only use the prescription part.
Okay, but it's the same data set that you use to generate the synthetic data. You didn't split it into two and generate it your models with one and then with the synthetic data set with another?
No, we just extract from the real data with this prescription, then we generate more prescriptions. And then you train the model with this augmented synthetic data. Yeah.
Perfect. Thank you.
Thanks very much.